very broad in theoretical computer science, mostly focusing on algorithms for massive data sets and data streams, parallel algorithms, about many other exciting topics. Now, thank you. I'll give the floor to Nguyễn.
Yeah, thank you. Thank you for the very kind introduction. So indeed, a lot of my work is on data streams and other things. But since I'm giving a talk at Brown, so I thought maybe I should talk about some topic that I feel maybe a nice topic here, which is on high probability bounds, right? Randomized algorithms. So so I'm going to talk about stochastic gradient method and some of the high probability bounds that we recently showed. So the setting that we look at is going to be, let's see, it seems to work, but okay. Maybe my computer, okay, it's just a bit slow. Right, so the setting we're looking at is in optimization. Abstractly speaking, you're given some function and some domain, and you want to find the solution that minimizes this function inside the domain. And gradient method is one among other methods to solve this kind of problem where you want to minimize this function given access to the gradient of this function f, or the subgradient, or some generalized gradient to these functions. And there are a whole bunch of different methods in here. Right, so you've seen gradient descent. There are also mirror descent. There are also accelerated gradient descent. There are also adaptive algorithms where in this other method you have to set the step size depending on the problem parameters. A lot of the time your problem could be almost like a black box to you, like a neural net or something. You have no clue what is the smoothness of the function or any other parameters. So there's these adaptive algorithms that sort of try to adapt to the geometry of the problem so that you don't have to pick these parameters like Adagrad or Adam and so on. So these are all methods that are based on gradients. So these kind of methods are very popular nowadays because they are very widely applicable to many scenarios, and the memory cost is pretty low. Generally, you only need to store solutions and the gradient, whereas some other methods such as cutting planes and second order method, right? A lot of the time you might need quadratic memory in the side of the problem, and that is not applicable when you have a big instance. So for these kind of method, if you are a theoretician, you could ask, okay, so what are the conditions required for you to find the minimizer? Right? So there are a lot of things that you look into. For example, is a function convex or non-convex? Is the function smooth or non-smooth? What is if the function have gradient, right? Is the gradient bounded or not? Right? What kind of access you have to this function? Maybe stochastic access. Maybe you have deterministic access to the function. So under different kind of condition, we'll have different kind of convergence bound, right, for the gradient methods. And furthermore, right, a lot of the time you care about the convergence rate, right, how quickly you get to the optimal solution. But there are also other considerations you want to look into. Sometimes, right, if you have a stochastic access to the function, you want to understand what is the failure probability of the algorithms. Does it succeed with high probability, or do you have to run it many times? And another pretty difficult topic, but of great interest, is generalization. Right? So a lot of the time your data is drawn from some kind of distribution, and you want that the solution that you find generalize well to the whole population instead of just the empirical loss. So that would be another consideration, which I will not talk about today, but it certainly is of great interest, and we also have some other work that look into this. And also, I should also mention that in many scenarios, we cannot find the minimizer. For example, if the function is non-convex, then generally it's very hard to find a minimizer. So a lot of the time you relax the problem. Instead of finding the global minimum, maybe you find some kind of approximate stationary point, right? So find the point for where the gradient is close to 0, for example. Or you could have some other notion of stationary, right? Maybe you want right, if you have access to the second order derivative, right, you want the second derivative. to be close to 0, or some other higher order notions, right? So these are also considered by a lot of people. So for the purpose of this talk, we'll just look into the convex case where you can find the minimum, or in the non-convex case, the stationary notion that I'm going with would be the point with gradient close to 0. Right? Of course, it still could be a saddle point, but since here we only look into the first order information, I'll not go beyond that notion of having gradient close to 0. Right? So right, so that is the setting that I'm in. So to further set up, I'll just quickly remind the audience of the setting that we look at, right? So here I'm having a function f, right? So here's the plot of the solution and the value of the function. So it's just a 1D problem, right? So the function that I'm looking at is assumed to be differentiable, right? So that I have the gradient, right? The theory also extends when you are not differentiable and you have subgradient. But let's just assume that the function is differentiable. So an important case that we'll look at, actually most of, probably 2/3 of the time, I'll focus on the convex case, where the function is convex, and you can see this is the pictorial description of convex function, right? So the function is convex. If you take a point and you draw the gradient, you would see that the linear approximation described by the gradient is a lower bound for the function, right? So this is the linear approximation, and it's a lower bound on the function everywhere. Right? Even if you're very far away, it is still a lower bound. So that is an important case, because you can say something about the global picture even if you just look locally, right? So that's why it is a very powerful assumption that if you have a convex function. And the second important condition that I'll look at sometimes is smoothness. So what smoothness say is that here is your function, and smoothness says that if you take your any given point here and you take the quadratic approximation, right? So you take the linear approximation and then you add a quadratic term to it, it is an upper bound on the function everywhere, right? So L smooth here, right? One way to describe it is to say that the gradient cannot change faster than L times the movement, right? Another way to say it is to say that you can get a quadratic function that is an upper bound on the function everywhere, right? So if you have a function that is both convex and smooth, the function is sandwiched between the linear approximation described by the gradient and the quadratic approximation, which is the linear approximation plus this quadratic term depending on the distance. Right, so these two conditions together are extremely powerful because it tells you something about the function everywhere, even if you just look at the local information at just one point here. Right, so an alternative property that we also sometimes use, right, if the function is not smooth, is that the G-Lipschitz condition. Here we just assume that the gradient is bounded everywhere in the domain by G. Right, so this is an alternative. So generally speaking, if you have convexity and smoothness, that is the nicest case. And if you have convexity and bounded gradient, then maybe that's also nice, but not as nice. Right? So that's the second case that is also good, but not as nice. So I'll actually focus mostly for now on the setting where I have a convex function and the gradient is bounded. But I'll not talk about the smooth case for a bit, because the smoothness is very nice condition and it get you better algorithms. The downside with it is that because you can get a better algorithms, the analysis is a bit cumbersome to fully exploit it. So to make the picture simpler, I'll just focus on the case where the function is convex and the gradient is bounded, because there the situation is a bit simpler. The algorithm is not as fast, but it's simpler, so it's easier to talk about it. Right. So gradient descent algorithms, like the simplest one is very simple. You just start somewhere, right? Because very low memory. You just need to store a solution, and you have some step size, and you just repeat the step where you move in the opposite direction of the gradient, right? Which is the step size eta that you choose. Now, of course, you could change the step size over time, and that actually is used in practice as well. But for the purpose of this talk, I'll just have a fixed step size throughout. Right? I'll mention briefly that you can vary this as well. But for now, I'll just have a fixed step size. And we want to understand the behavior of these algorithms. Right? It's really simple algorithms. But we want to know, right, does it converge? And if so, with what failure probability? Okay, so here's the, I should mention the stochastic version. So the algorithm we just described just now is the exact version. But a lot of the time, evaluating the exact gradient is very expensive, because if you have a massive data set where the loss is the sum of the loss over all the training examples, then to compute the exact gradient, you would have to compute the gradient on every single example, and you add them up, which is very expensive. So a way to get around that a lot of the time is you, instead of evaluating the exact gradient, you have some estimate, some noisy estimate, right? Which is, for example, you just take a small subset of training example as samples, and you evaluate the gradient on only the subset, right? So the gradient on the subset would be your estimate GT here, right? So that is the idea, right? Pretty natural idea, right? If you work in theory, right, you just taking samples. So the nice property of taking the sample like this is that it's unbiased. So the expectation of the estimate is the true gradient. And a lot of the time we just assume that the error, like how much deviation you have of the estimate compared with the true gradient, is not too large. And this is verified for, I think, many settings, especially say the vision setting, where you see that if you take the second moment of the deviation, then it is usually bounded by some quantity. Let's call that sigma square. So sigma here is sigma square is the variance, right, of the estimate. And this model of error will play a crucial role when we talk about what is the failure probability of the algorithms. But this is the usual definition, where you just take the variance and you call that sigma square. Now, if you have more assumption than this, then hopefully we'll get better concentration behavior, right? Lower failure probability. And if we have weaker assumption than this, that maybe the second moment is not bounded, which could also be true in some scenario. For example, if you have language tasks, the error actually have pretty heavy tail, then maybe our conversions would be weaker, and we'll look into that as well. Right? So stochastic gradient descent is exactly the same as gradient descent, except that instead of having the exact gradient, I have only the estimate GT. So I can only move in the opposite direction of the estimate GT, right? I cannot move in the direction of the true gradient. And if we look into the conversions of stochastic gradient descent, so this would be the kind of guarantee we have for the case of convex function and Lipschitz. So basically, if we look at the gap between the solution that we can produce versus the optimal solution, the rate that it go down will be roughly 1 over square root of t. So t is the number of iterations that you have. G is the bound on the gradient length, and sigma is the standard deviation of the gradient estimate, right? So this is a guarantee you get if you have a convex and Lipschitz function. Now, if you have a smooth function, then gradient descent will get you a better convergence, right? The smoothness is a very strong assumption because it says something about the function everywhere, right? Not you just look locally, but you know something everywhere. So it's a very strong assumption, and you get the convergence rate that's scaled by 1 over t instead, if the variance, if the noise of the gradient estimate is very small, right? So let's say if the sigma is really tiny, right, then you can ignore this term and you would get a 1 over t, right? However, if you have as the noise get bigger and bigger, your convergence will get worse, and you get back to the 1 over root t, right? So you get exactly the same term as here, but you have the chance that if the sigma is very small, you can get the convergence to be 1 over t instead, which is better. So this again is also the classical in-expectation bound for both of these. And finally, if you have a general function with no convexity assumption, and here the goal is just to find a point with small gradient, then here of course you need some kind of smoothness assumption, because maybe there's no point where the gradient is 0, right? You could have a function, for example, f of x equal to absolute value of x, right? You don't have the gradient being 0 ever. It's either 1 or minus 1. So you cannot find a stationary point. So you need some kind of smoothness assumption for the point with gradient 0 to even exist. So in that case, you can find a point where the gradient is close to 0 at the rate of roughly 1 over t to the 1/4. So here I'm writing it in terms of the square. So the square of the gradient is 1 over root t, but if you look at the gradient length, it should be 1 over t to the 1/4. So it is a worse rate, right, than the convex case. You can see that the convex case, we get 1 over root t, or we get 1 over t. For the non-convex, we want to find approximate stationary point is 1 over t to the 1/4, which is a bit slower, quite a bit slower. And here I'll just drop all these other terms, but technically there are also these terms depending on the initial distance to the optimal solution, the smoothness, and sigma, and so on and so forth. So I only keep track of the dependence on t here, which is, I guess, a common thing people do. But yeah, they are also here as well. The distance, the sigma, and L, and so on. So these are the classical bounds that they all, these guarantees are all hold in expectation, which is very nice. And then you can ask, okay, so if we want to look into the probability of failure of the algorithms, then what can we say about these algorithms, right? So let's say that I have a failure probability of delta. What can I say? So the simplest thing that you can always say is that you can apply Markov's inequality, right? You know the expectation. So if you use Markov's inequality, you will be able to get a guarantee or with dependence of 1 over the failure probability delta. And this guarantee is nice because you could just use the in-expectation bound immediately. However, the downside is that the guarantee is usually pretty weak, and it would suggest that if you want very small failure probability, you might have to do the usual trick of repeat the algorithm many times and find the best one, right, to get the high probability. And this is something that is not really done in practice, right, because each training run could be very expensive. So generally, people don't train many times and take the best one. So that's too expensive. So the question is, okay, this is already done out there. So can we actually show that this is true, that this gradient descent method have very low failure probability? Right? So ideally, we want the failure probability, the dependence of the guarantee on the failure probability to be logarithmic in the failure probability, right, as opposed to linear, right? So instead of studying the first moment of the error, can we understand the higher moment of the error, right? Now, this would allow us to say that even if you run the algorithm on a small number, maybe just one run, you already have very high chance of success, and this is already empirically observed. So, so can we show that this is actually the case? That, right? If you just run once, maybe your failure probability is already extremely small. Right? So it is the common knowledge, right? That gradient descent is very robust, and here we really just wanted to provide some kind of mathematical proof of this sort of known fact. And the intuitive idea is that the algorithm sum up a lot of information along the way, and even if you get some mistakes along the way, but if you add up, right, sometimes you make mistake, you go in the wrong direction, and sometimes you go in the right direction, but as long as you keep have a bias toward the right direction, maybe eventually you will converge after many steps, right? And the intuition is, right, at least for me, is something like this. If you write down the difference between the final solution versus the original solution, right, it is simply the sum over all time steps of the change that you make, right? And the change that you make is simply eta times this gradient estimate gt, right? So ideally, right, this is sum of random variables, and each random variable we assume the gradient estimate to be unbiased, right? The expectation of the gradient estimate gt is a true gradient, so it has the right expectation. So this kind of summation is very familiar to people doing theory, right? If you have these random variables that are independent and they all have the right expectation, then you would expect that it follows some kind of law of large numbers or some behavior like some kind of Hofding Chernoff bounds kind of behavior, right? Sum up random variable with the right expectation, you should get the conversion, right? The concentration. So the question that we ask when we look at this is that can you actually prove some kind of Hofding or Chernoff bound for the conversions of these gradient method, and can we do so in the same general condition where gradient descent is applied, right? So I mentioned the set of problems that we looked at earlier, right? You just need a couple of assumptions, right? Convex and smooth, right? You want some results. If you have convex and bounded gradient, you get some results, right? So it's very generic setup. And we ask, okay, can you get this kind of the Hofding or Chernoff-like bound for these algorithms under the same general setting, right? So indeed, that's what we did, which is we show sort of like the Hofding-like bound for the conversions of gradient descent, and this bound actually hold for all the methods that I mentioned earlier. So you could have stochastic gradient descent, you could have accelerated version where you have faster conversions. It also work if you look into adaptive method where the algorithm doesn't know the smoothness but adapt to it, so-called undergrad. It also work for certain setting as well. And the model for the noise for us, we mentioned earlier, right? We have this noise, and you need some kind of assumption on the noise so that you can show concentration. And here we'll look at the pretty general model where the noise is assumed to be sub-Gaussian. That means that the noise would follow a distribution, I guess it's bounded by the Gaussian distribution. And the bound would be pretty tight in the sense that if you put in the failure probability to be constant, right, let's say 10%, then you would get exactly the same bound as the in-expectation bound that we had earlier, right? So if you plug in the failure probability to be 10%, you get exactly the expectation bound. So it exactly matches the thing if you would get with Markov with a constant. But if you want the failure probability to be extremely low, then you would get a dependence that is like a logarithmic in the failure probability in a similar way to the Hofding bound, right? And we'll also have an extension to the heavy-tailed noise, but there you have to change the algorithm a little bit. And there's a good reason why you have to change the algorithms that we'll discuss when we get there. But we also can extend to the heavy-tailed noise as well. So let me quickly mention the previous work in various different settings. So in the convex case, we would look at the mere descent accelerated version of that. The previous results get the similar results, but it requires that the domain of the that we're optimizing over is bounded, and the bound will depends on the diameter of the domain. Right? So if you recall, the results for in expectation does not care about the diameter of the domain. And in fact, you want to exploit the initialization, the distance between the original solution and the optimal. Right? So if you have a really great initialization, you want to converge faster. And this kind of bound, depending on the diameter of the domain, does not capture that. So instead, we get a bound that is similar to the in expectation bound. You don't care about diameter, you care about the initial distance. In the non-convex setting, there are also a lot of previous results, and the main improvement there is in this factor where previous results have a factor of log of 1 over the failure probability times log t, and instead we have the sum of the two terms instead. And furthermore, we also extend the results to grad where the algorithm is these adaptive algorithms that I guess some version of this is commonly used in practice, so-called Adam. You can prove things for Adam as well, but for our simplified exercise, we mainly just focus on the grad, which is I guess more theoretical version of related to Adam. So previous work requires some additional assumption, and we do not require such assumption. There are also the so-called, in practice, when you perform this adaptive method, they actually divide so the solution is really high dimensional. And what you do actually is you realize that every coordinate will have a different smoothness, and you want to utilize per coordinate smoothness as opposed to using smoothness across, because that's like a much worse bound. And this kind of results actually is also used in some of the work in solving linear systems and max flow. Right? You care about the per coordinate smoothness because they are actually a tighter bound than using the worst across all coordinates. So we can also do that for the grad per coordinate algorithm as well, which was not done before. Okay, so that's that. Okay, so let me quickly get into the setup of the proof. Right, so here is some background. So here is the amount of noise you have in time step t, which is the difference between the gradient estimate and the true gradient. And if we look into the difference between xt and x0, right, it is the sum of these gradient estimate times the step size over time. And you can decompose that into what you really want, which is the true gradient, plus the noise, right? And ideally, we want to show that the sum of, intuitively, we want to show that the sum of the noise is small, right? Right, and you need them to be well-behaved. Each of the term has to be well-behaved for the sum to be concentrated. And what we assume is that the noise will be sub-Gaussian, right, which I said before. And one important property of being sub-Gaussian is that if you sum up things that are sub-Gaussian, you get back a sub-Gaussian thing, right? It's a generalization of the fact that if you have a lot of Gaussian random variable and you add them together, you get a Gaussian random variable. So it's also true for sub-Gaussian. And now we can try to do the proof. Now the previous work generally go through some kind of black box application of Friedman's inequality. So here is Friedman's inequality. Intuitively, what it means is really because our sequence of random variable are not independent, but we assume that they have some kind of martingale-like structure, right? Condition on all the previous noise, the next noise have expectation 0. So the natural thing to do is to apply some kind of standard martingale concentration results. That is, you could think of it as like a Hofding-like bound, except that it's martingale as opposed to independent random variables. And the issue here with applying this bound, as we'll see, is that it requires a bound almost surely for each of these terms in the sum. And our sum is not really, we don't have an almost surely bound. on each of them. In fact, even just the noise itself is a Gaussian, but it's a minor issues. The bigger issue is that actually the term that we add up will actually possibly be unbounded. So we'll have to deal with these issues. And one way that they fix it in the previous work is that you will use some kind of union bound over all iteration. So you show that not just the final solution is bounded, but every step along the way, you're always bounded. And this would introduce an extra log t factor in the concentration, but will not do some kind of induction and union bound like this, which allow us to get the same guarantee as the in expectation bound. So let me go to the standard proof of gradient descent, and we'll see how you can lift that from the standard proof to the high probability proof. Right, so the usual proof proceeds something like this. So we apply the convexity condition, which says that right, the convexity said that the function is always bigger than the linear approximation. Right, so here it says that f of x star is bigger than the linear approximation evaluated at xt, and I'm just moving the x star from right to left and move the linear part from left to right. But this is really just saying that f of x star is bigger than the linear approximation. And I'm just rearranging the term, and here just observe that this is how much I move. When I move from xt to xt plus 1, I move proportional to the gradient. So I just substitute that in. And now if you trust me that I just rearranging term with equality, nothing changed because it's all equality, you arrange it into this form, which is the following. So the difference between f of xt and f of x star is this very nice telescoping term of the distance between x minus the distance between x star and xt plus 1 plus the gradient square. So intuitively, what is it saying? It is saying that right, the difference will be proportional to the gradient square, which we assume to be bounded. So this you could think is a minor term here. But the main thing to say is that the difference between fxt and fx star is the difference between two telescoping sum like this. So what you can do is that you are going to add up all of these equality from time 1 to time t. You get a nice telescoping. They all cancel out, and you just end up with a single distance. And so that is the proof. So now if you pick the right step size, you would get that the difference between the solution you find and x star would go down at the rate of 1 over t, right? Because you have t terms here, so if I take the average, 1 over t, I would get the distance square over t, right? So that is the convergence. So you can return either a random iterate among the solution you compute along the way, or you could take the average of the solution you compute. They're all good. So that is the classical analysis for the gradient descent. For the stochastic case, it is very similar. The only thing we need to do is that we have to add this stochastic noise into the analysis and propagate it through. So in the convexity, it's like that, but I'm moving by gt. I'm not moving by the true gradient, so I have to split off gt and the noise, and then I do the same analysis as before and propagate everything through. Have this the same as the thing you want, plus this error term that depends on the noise. So you have to take care of this error term now, right, due to the noise. And the error term would have two parts, where the one part is the noise square, which is not a big deal. It is a Gaussian, so the square is also exponential random variable. It's not too big. The main issue is on this term, the product of the noise and the distance and the vector connecting your solution and x star. And this intuitively is true, because you could think of it, even if the function is just x squared. If you're really far from the optimal solution, just having a tiny error would change the function value depending on how big you are, right? If you have 1,000,000 square, now you become 1,000,001 square, right? The solution only changed by 1, but the function value could change by a lot if you were start out at 1,000,000. So this noise here is technically unbounded. It depends on how far you are from the initial, from the optimal solution. Now this is where the previous work just assume away the problem by just assume that the domain is bounded. Right? So if the domain is bounded, then this is bounded by the diameter of the domain, and everything go through, right? Because you have a bounded term. Now, if you don't have the bounded domain, then one issue that could happen is that even though you could start out near the optimal solution, if you make a few mistakes earlier on, your solution could move slightly further away. So a priori, there's no bound. Right? Even if this happened with only a low probability, we do need to take care of it because we care about high probability. Right? So we really might encounter the case where you are unlucky for the first few steps. So the change that we did is that the following. So we look at this term that we need to worry about, and we see that this term here, even though it has this dependence on xt minus x star, the dependence is only linear, whereas the entire expression actually contains these terms that are quadratic function in x star minus xt. So intuitively, if this distance is really big, we're going to have a linear term that could be big, but we'll have a quadratic term that is even bigger, right? So we can use the quadratic term to bound the linear term. So the standard in expectation proof just add up everything with coefficient 1 so that they telescope. But what we can do is that we are going to change the coefficient of this quadratic term so that the coefficient actually will go down over time. So we sort of, every step we take a little bit of the quadratic term to compensate for the linear term. So the coefficient will go down slightly over time, and we just need to make sure that initially we have enough of the quadratic term so that we lose a little bit every time, but we have enough at the end so that the change in the quadratic term is not too much, and that will be sufficient as well. So that is what we did, and we take the martingale where this is what happened in every time step. I'm really just shuffling the terms so that I put all of the noise-dependent term on one side and all the other term on the other side. And then I just add up this noise-dependent term in my martingale. So my martingale is really just a sum over all time step of the noise term with a little bit of extra. Now the time step t would have a certain weight wt, where before it was all 1, but now I will have a different weight on different time step, and the intent is that the weight will go down over time, and I also add a little bit of an extra quadratic term. So this quadratic term is used to compensate for the linear term. And this quadratic term will be unimportant. We will be able to compensate for that from the Wt. So the proof is pretty natural at this point. You have this property of the Gaussian random variable. If you take the expectation of the moment drifting function e to the x times some value, then it's always at most e to the that value square times the sigma square. So you just apply this to this the dot product that we have, and if you take a look, you'll see that it exactly match up. That if I take this random variable and I take bounding the moment drifting function of this, you would see that I have the Wt square, which is this part. I have eta square, which is this part. I have x star minus xt square, which is this part. And finally, this random variable is assumed to be sub-Gaussian, so I get the sigma square part. So this quadratic term here is exactly that moment drifting function part for this noise term. And all I need to set up is that I need to set up the WT so that as I go back, the coefficient get bigger by this sigma square eta square WT square, so that I can cancel out in the telescoping sum. So the WT will be big at the beginning, and it gradually gets smaller. The amount it gets smaller is by this sigma square eta square W square. And then you can, of course, choose this coefficient so that, roughly speaking, it starts out with some value, and at the end, it dropped down to, let's say, half of the original value. So all the WT, even though they change over time, they're all within a constant factor of each other, say a factor 2. So you get the same concentration if you ignore this factor 2 drop in the coefficient. So that is the proof, right? So you will fill in the standard argument with the moment generating function, but with this weight that drop over time, then you would get the concentration to go through. So we have several extensions to this. For example, if you have unknown time horizon, sometimes you have to set the step size differently over time. So this can also be done in this framework. You could have varying step size, there's no problem. As I mentioned earlier, if you have smoothness, actually accelerated algorithm is even faster. And the proof also works for accelerated algorithms. So you can use accelerated gradient descent to get the 1 over t square rate for convex and smooth function as well. We also look at some other version of this where, let's say, you have constraint, right? So far I work only with unconstrained setting where how much you move is exactly the gradient. We can also do the constraint setting with, say, projected gradient descent or mirror descent. They also work. So the proof technique is very adaptable, right? So again, right? So sometimes you prefer to use adaptive algorithms that can adapt to the smoothness, and the technique also works for the other graph setting. So I'm going to skip this next section about the non-convex case. So the main message here is that in the non-convex case, the proof is actually very similar, but I would have to review the standard proof and point out what happened in the standard proof. But the main thing that one need to observe is that in the standard proof of the smooth non-convex function for the inexpectation proof, the same kind of error term would show up, because again we have this term depending on the noise multiplied with some quantity, and that quantity could be big or small, but in this case actually even small, because we are having a point with gradient going to 0. So it's actually even easier than the other case. So you can use the same martingale, similar martingale to the convex case, and you can get the same kind of guarantee as in the expectation case. So I mentioned earlier that sometimes we also care about heavy tail noise, right? So if you have like a language model, right, then you sometimes see that the distribution of the noise is not as nice like a normal distribution. So sometimes when you ask, okay, what kind of bound can you show if the noise is even heavier? So a common assumption could be something like this, where we assume that the noise is bounded in p moment, where p is some number between 1 and 2, but it need not even be bounded. The second moment need not be bounded. Right? Maybe you only have a 1.1 moment bound. So can you still show some kind of concentration? And this by itself is not sufficient, because even in the case where you just sum up these random variables with bounded 1.1 moment, you're not going to get a Gaussian-like concentration. So there's no way you can prove such a thing. So the fix here for us is that we're going to use the clip gradient descent. So what does it mean? So when you do clip gradient descent, you add this clipping term like this. So basically what it says is that if the gradient, if the estimate GT is very long, then I'll clip it to a certain length lambda t. If it's shorter than that, then I keep the estimate the same, right? So this is how you do clipping. So generally, it just says that, you know, if in the unlikely case your estimate is really big, I'm going to truncate it to a smaller length. So the problem with this clipping is that it introduces some bias. So you avoid the problem with the noise, but you do introduce some bias into the problem. And you would have to be a bit careful on how to choose the bias, the clipping parameters, so that you have simultaneously a bounded variance, but also the bias is not too big due to your clipping, right? So ideally, this is like a trade-off, right? Because if you have clipping to be infinite or not clip at all, then you have no bias, but you could have huge variance. But if you clip it, you reduce variance, but you start introducing bias. So you have something that is sort of balance between bias and variance. And you can do this and get these kind of high probability bound with the optimal convergence rate. So the optimal convergence rate for the bounded p moment turns out to be these kind of expressions that depend on p, and there are lower bounds saying that these bounds are actually tight, so they are a bit weird. For the convex case, the rate turns out to be t to the 1 minus p over p. So for example, if you go back to the standard setup with p equal to 2, you get t to the minus half 1 over root t we talked about earlier. And for the non-convex case, if you put in a p equal to 2, you get minus, whatever it is. Yeah, minus 1/2, I think. Also true for the square of gradient. Yeah, so these are matching the lower bounds, and unfortunately, the bound here is not as nice as in the sub-Gaussian noise case, because now we have to set these clipping parameters, and we can have some bound when the clipping parameter does not depend on various problem parameters, but the bound are a bit worse in the constant. So the dependence on t are the same, but the other dependence are worse. And it also feels a bit strange that we need this clipping to be so precise and dependent on so many parameters of the problem. So it would be nice to be able to improve this. So the idea is still using some kind of martingale. And now one challenge is that I will not go into the proof, but basically because of the clipping, it introduced some bias, which will introduce error proportional to the gap between the function value of the current solution and the optimal solution. And now we have to account for this in our decreasing coefficient. And the idea that we use is that we use a maximum of the gap or an upper bound on the maximum, which will allow it to change in a monotone fashion, because the gap could change up and down. Ideally, it is a monotone down, but because it's stochastic, you can never guarantee it. So we use a max over time, and this seems to fix the problem and get the proof to go through at the cost of maybe not ideal dependence on the constants. So I'll briefly mention some interesting questions that are left open. So it would be nice to be able to get all the same results for the clip algorithms as in the algorithm for the sub-Gaussian case. We get for many of them, but for some setting like constraint with accelerated gradient descent, it seems a bit tricky. I don't know how to do it. And another observation is that clip algorithm might be something to do in theory, but it's not the best in practice, right? So in practice, maybe people prefer to use this kind of adaptive algorithms like Adagrat or Adam. They sort of having some kind of soft clipping behavior, and generally people use this algorithm rather than clip gradient descent if they can. So what kind of conversion guarantee do you have for these algorithms? They're also remarkably robust in practice. So we don't know how to prove this because the step size now have a lot of dependence on the stochastic gradient, which makes the analysis quite tricky. But I think this is an interesting question. That's all I have.
All right. Yeah, we have some time for questions. So sometimes people just put this log 1 per delta in the size of the mini batch, which also. So I was just imagine if I just put like a union bound over how far off that each estimate can be to the true gradient, and right. So if one of them can fail with probably delta, now I have t iterations.
Yeah, so I think, but that means that you would have a bigger mini batch, right? So the number of gradient query might go up, or are you? Yeah, so I think.
Trade-off, right? Because if I can get away with fewer iterations but blow up by the size of my mini batch by some log factor, then maybe that's fine as well. Like, isn't the right metric to look at is the total number?
Yeah, if you look at the total number, yeah. Yeah, but you are right that it is true that some kind of trade-off, at least in terms of the theory bound, is possible. That I guess the question there would be, how big can I make the mini batch while still retain the same conversion guarantee, right? Because you save in the parallel time, right? So maybe the total number of gradient query is the same, but you sort of compress it in what is the most parallel version of it you can make.
In your work, you kind of did not. You just said that noise can be sub-Gaussian, for example, or
yeah. That is true. That is right. Yeah. So, yeah, I think the similar kind of proof would work if you ask, how much you can compress, get bigger mini batch, fewer iteration, how much you can get, and people do look at this. Yeah, you are right. Yeah.
So I guess when you're describing this trick where you steal like the decreasing amount of mass from
Yeah.
quadratic.
Yeah.
You were talking about how when people assume that it's bounded, it's all very simple because you can just assume that the distance between like if the whole space is bounded and the linear term is bounded.
Yeah.
Is there any hope here for just like doing something more direct and just trying to like understand how the linear term is distributed and then argue that even though it might not be bounded, it's like has a very low probability of being large and screwing up this kind of argument? Or like is that like well behaved probabilistically under these noise assumptions?
Yeah, so it in some sense it is well behaved. So I think maybe what you're getting at is so some of the previous work also sort of look into something like this, where they don't assume the bounded domain, but you analyze the probability that you make mistake and go too far, right? So you say that I have this implicit radius that I want, and if you ever stray out of that radius, and I declare failure, and that also is a decent approach. The main thing that is different between that and ours is that this would require some kind of union bound over all time step, that you never step out. Now it should be true in the martingale that if you look at the probability that you ever step out at all, it actually is the same as you look at just the final step. But proving such a fact seems quite tricky. Because somehow you still have to. But the most naive union bound would lose a log t. That's what other people did, and you are right that it is actually better behaved, and in some sense we sort of show that by having this moment rating function bound. I'm not sure what else to say, but that intuitively the probability ever stepping out at all is the same as the stepping out at the end, but don't know how to show that. Yeah.
Some of my, since I've been doing ad hoc version of, but not necessarily this proof, but sometimes maybe
Yeah.
SAT gradient. But sometimes maybe you initialize in a saddle-free region and this support, like in this region there are no bad filter. But once you step out of this region, there are spurious optima. So you want to stay in this region, and sometimes we suffer from the same issue that it's like there's only very naive ways of bounding that you never step out of this region.
Yeah. Yeah. I see. Yeah, so it is efficient in the sense that it is pretty tight, even if you drop along the way. This really just try to get in the, let's say the last log t factor. But if you okay with dropping a log t factor, I think this truncation trick is really simple. Yeah.